Hello, chemists! This is Ms. Placino, and you are watching lesson 1.6 on isotopes and average atomic mass. In today's lesson, we're going to talk about what isotopes are and look at the impact that they have on the average atomic mass of an element. So we've got a couple goals for today's lesson. First, we're going to explain what isotopes are in terms of subatomic particles. We're going to understand how isotopic abundances are determined. And finally, we're going to calculate the average atomic mass of an element based on isotopes and isotopic abundances. This is the big one for today, and we'll be spending some time looking at a practice problem or two where we do some calculations. All right, lots to do today. Let's get into the lesson. So on the screen right now, you've got 3 nuclei from 3 different carbon atoms. What I'd like you to do is pause the video, figure out what they have in common and what's different between them. Hopefully you didn't go through and count the individual protons and neutrons in each of these nuclei. Based on the notations, you should be able to quickly figure out the numbers. Since it's a carbon atom in each of the 3 cases, you should have 6 protons in the nucleus. It's the number of neutrons that are changing. In this atom of carbon-12, there are 6 neutrons. In carbon-13, there are 7 neutrons. And in carbon-14, there are 8 neutrons. We can do that math very quickly. Atomic mass minus atomic number tells us number of neutrons. These 3 nuclei represent 3 different isotopes of the element carbon. All an isotope is an atom of an element that has the same number of protons, but a different number of neutrons. So since they've got different numbers of neutrons, they've got 3 different atomic masses. In the previous video, we talked about using the periodic table to find atomic mass. And carbon, if you were to look it up again, it's 12.011 U. We know that there have to be whole numbers of protons and neutrons in the nucleus. Those are the 2 subatomic particles that contribute to the mass of an atom. So you might be wondering, well, where does this come from? Where does that 0.011 in the case of the carbon atom come from? And it has to do with the different isotopes. So most of the carbon atoms on the planet are carbon-12, with 6 protons and 6 neutrons in the nucleus. A much smaller quantity are made up of carbon-13 and carbon-14. But if we were to take the average mass of a carbon atom based on the percentages of carbon-13 and 14 that are present, we're going to end up with an overall average atomic mass slightly above 12 AMUs or 12 Us. You might be wondering, well, how do we get that information? Do we send out a team of freshmen to pick out every carbon atom and go through and count the protons and neutrons and see what the isotope? No, of course not. That is impractical and also impossible. We're going to use a piece of equipment called a mass spectrometer to figure out the abundance or the relative amounts of carbon-12 to carbon-13 to carbon-14. And this is how we find average atomic mass. So in the next slide, I want to show you a quick video on how the mass spectrometer works.
Instrument in many kinds of chemical analysis. But how does it work? And how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then it is ionized. Third, it is accelerated. Fourth, it is deflected. And 5th, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer, we use electromagnets to try to deflect the ions off their path. The amount of force that the ion feels from the electromagnet is proportional to its charge. The path that the ion actually takes is a result of its mass-charge ratio. A different particle with a different mass-charge ratio will take a different path. And this is what we are actually detecting, different mass-charge ratios. So let's analyze a sample. If we vaporize it and ionize it, accelerate it, deflect it, and then detect it, we can record its mass-charge ratio. If we repeat this with more of the same sample, we will record different size fragments. Eventually, we'll know the proportions of all the different size pieces in our original sample.
Let's talk a little bit more about what's inside the mass spectrometer. We know there are 5 different steps. First, we have vaporization. So we take our sample, we get it into the machine, and it is heated up and turned into a gas. That's what vaporization means. Second step is ionization. So we're going to ionize the sample. We hit it with an electron beam source, and that's going to take our neutral particles with no charge and turn them into ions. We kind of break apart the sample, and you end up with charged particles. We're then going to accelerate the ions. And we know, based on the video, that the ions would want to move in a straight path based on their mass. But eventually they hit an area where there's an electromagnet, and that's going to cause the ions to kind of deflect or bend their path. The amount that they are bent is based on their charge. The more highly charged the particle is, the more its path will be disturbed. And finally, the particle is going to hit the detector, and that's going to be based on the mass to charge ratio. Don't panic if you're feeling a little bit lost. Just kind of want to give you the general overview of how this piece of instrumentation works. Don't worry, we are never going to see this in the lab. This is well beyond a high school course, definitely more of an upper level college course where you'd see an instrument like the mass spec. Okay, what I want to look at is the results we'll get from a mass spectrometer. Let's say we're analyzing a sample of zirconium. It's this metal here, Zr on the periodic table. After I've analyzed the sample, I'm going to get a graph that looks like this from my mass spec. Along the x-axis, we've got atomic mass and U, and on the y-axis, we have relative abundance. That's just a percentage. Sometimes you'll hear this referred to as percent abundance or isotopic abundance. It's all one and the same thing. It's basically telling us, okay, out of all the zirconium atoms that I sampled, what percentage had a mass of 90, 91, 92, 94, and 96 U? Based on the graph, you should be able to determine that zirconium-90 is the most abundant isotope of zirconium, and that there are 5 major isotopes of zirconium. I know that its average atomic mass has to be somewhere between 90 and 96. And it turns out for zirconium, it is about 91.224 U. The big key for today's lesson is learning how to take this data, this relative abundance and atomic mass data, and turn it into the average atomic mass for a given element. So let's clear up some definitions and then get into the calculation. When we go to determine atomic mass, we need to use the relative abundance or the isotopic abundance. And that's just telling us the relative percentage of the isotopes of an element. It's worth pointing out that we use only the naturally occurring isotopes, the ones that we would find in nature, not ones that have been artificially produced in the lab. We'll look at a simpler example than the zirconium that had 5 isotopes. Let's start with something like rubidium that has 2 major isotopes. Rubidium, which is Rb on the periodic table, comes in mass of 85 and 87 U. Based on my mass spectrum, I can see that 72.16% of all rubidium atoms have a mass of 85 U. The remaining 27.84% have a mass of 87 U. I want to use this data to determine the average atomic mass of rubidium. We do this by taking a weighted average. You might know how to do this already. Whether you do or you don't, I'd like you to pause the video and try it out. You have a built-in check for your work. If you look at the periodic table, you can find rubidium. That's all the way over in group 1, all the way to the left, element 37. Its average atomic mass is 85.47 U. So try it out, and we'll go through this together in just a minute. All right, hopefully you've given something a shot, but let's look at it together. So we've got rubidium 85 and rubidium 87. Now, in reality, you end up with atomic masses that are slightly lower than the mass number provided, but our technique's going to be the same. We're going to find the weighted average, and that's going to involve taking the mass of the isotope and multiplying it by the relative abundance. So really, oops. Call that relative abundance RA. I'm going to repeat that for every isotope that exists naturally for this element, in our case, rubidium. So now I'll take my 86.91U, I'll multiply it by 27.84. What do you think I need to do with those two numbers? I add them together. I'm going to divide by 100 because those are percentages. And I should end up with the average atomic mass of rubidium. I calculate 85.46U, which again is extremely close to what we've got in the periodic table. You might have gone through and taken the percentages and first converted them into decimals, completely fine, then you wouldn't need that divide by 100 step at the end. But check your work, make sure it makes sense. We've got to be somewhere between 85 and 87, we are. And again, use the periodic table to make sure you've got it right. Let's try another practice problem. Okay, here we are with the practice problems. I'm going to do one that's slightly more complicated than what we just did. Let's go ahead and look at question 2 in the practice problems. Magnesium has 3 isotopes. Excuse me. You're given information about the mass and relative abundance, and you're asked to find the average atomic mass of magnesium. Hopefully, since we've been through one problem together, you can pause the video and figure this one out on your own, and then check back when you're done. So pause it, give it a shot. All right, I'm not too worried about seeing the formula for something like average atomic mass, but what you want to do is take the mass, 24U, times the abundance. I'm going to turn these into decimals right away. And you're just going to add them up. 25U times 10%. And 26 times 11.01. Make that a little bit smaller so I can get it all on the screen. Just gonna grind through the calculation, making sure that I'm entering the numbers carefully. It's really, really easy to make a small mistake and end up with something that's like way, way off. But when I do the calculation, I end up with 24.3207U. Sanity check. I'm somewhere between 24 and 26. Yeah. The 24 isotope is the most abundant and pretty close to 24. Good. And finally, I can check the periodic table. Magnesium on the periodic table is 24.305U. Plenty close enough. I'm not off until I get into the hundreds place. I got other practice problems to play around with as well, so hopefully you feel confident doing that. Let's get back to the lesson. The last thing I could ask you to do with isotopic abundance is a little bit more advanced. So what we're used to doing is taking the atomic mass and the isotopic abundance or relative abundance to calculate the average atomic mass. To make it a little bit more difficult, I can give you information about the isotopes. I can tell you there are boron 10 and boron 11 isotopes. So the two real common ones for boron. And I can ask you to find the relative abundances of each isotope. This is a little bit trickier. You might feel like I don't have enough information. I don't know the percentages. I don't know the average atomic mass. How do I figure this out? Well, while average atomic mass wasn't given, you can readily find it out simply by looking at your periodic table. Boron has an average atomic mass 10.81U. Pause the video, see if you can figure this one out. I will give you a hint that it really just takes some algebra, and it is math that you are more than capable of doing. So pause it, we'll come back and walk through your work with you together. Okay, I kind of jumped ahead and I started writing some stuff out. To solve a question like this, I need to take the average atomic mass and set it equal to the mass times the atomic abundance, or the isotopic abundance of one of the isotopes, and then add that to the mass of the other isotope times its relative abundance. I know that the abundance have to add up to 100, or if I want to work with decimals, have to add up to 1. I chose to work with 1. I think it's a little bit easier. Now it's just an algebra equation. I can go ahead and do out the math. Actually, I'm going to get rid of the u's just to not confuse them with the x's. I told you, the math itself is not particularly difficult, but conceptually, trying to figure out how to solve this problem, or how to set up to solve this problem, can be very challenging. For the sake of simplicity, I'm just going to go to the nearest hundredth. And if it's 0.19 in decimal form, I know that would be 19%. Last little bit that I have to do is figure out which isotope is present at 19% and which isotope is present in the remaining 81%. It matters. The best way to do this is to look at the average atomic mass of boron, in this case 10.81 U. Is 10.81 closer to 10 or 11? Yeah, definitely closer to 11. Boron 11 must be the more abundant isotope, so it must be at the roughly 81%. Boron 10, that's the 19%. And if you plug in the percentage times the mass and you add it to the percentage times the mass for the other isotope, you will wind up right back at 10.81 U. So these answers look good. That's definitely a little bit more complicated. If you were kind of stuck on how to do this and a little shaky with it now, don't panic. If you can do what we were doing with magnesium and rubidium, you're in really good shape. All right, that wraps it up for today. Thank you so much for tuning in, and I hope you found this helpful.